Okay, now that we've gone through arithmetic sequences and arithmetic series, we're going to take a look at the geometric version of those. And so this will go a little bit quickly because we've already covered some of the basics. And really what we're dealing here with is just different formulas and slightly different look to things. So let's look at geometric sequences. What is that? It's a sequence whose next term is found by multiplying by a fixed amount called the common ratio. So you remember in an arithmetic sequence we were adding a fixed amount called the common difference, D. Now we're going to multiply by a common ratio, R. And so let's take a look at a couple of examples and see what happens here. Here I have a sequence. My first term, a sub 1, is negative 1. And I have a common ratio of 3, R equals 3. So if I multiply negative 1 by 3, I get negative 3. If I multiply again, I get negative 9, negative 27, negative 81, and so on. Now here's where things might be a little bit different. If I start with a sub 1 equals 10, and I have a common ratio of negative 2, what's going to happen? Well, I'm going to multiply 10 by negative 2. I'm going to get negative 20. And then if I multiply negative 20 by negative 2, I get positive 40. Multiply by negative 2, negative 80, positive 160, negative 320, etc., etc., etc. And so the terms in this sequence are going to alternate positive and negative. And we actually call this an alternating series, which isn't terribly important for right now, but the idea is that here's an example of a sequence that does not go in the same direction. We have positive, then negative, and positive, and negative. But because it has a common ratio of negative 2, it does count as a geometric sequence. Now if we were just given this sequence, how could we get a sub 1 and R? Well, a sub 1, again, that's pretty easy because that's always the first term here. But in order to get the value of R, we want to look at what are we multiplying to get from one number to the next. So we could do this actually either way. We could start with, let's say, negative 9 and say, what do I have to multiply by to get negative 27? Well, of course, that's times 3. But you notice this says common ratio, and we usually think about division when we think about ratios. And so another way to do this would be to say, if I take this number and divide by the 1 in front of it, okay, now I'm dividing, negative 80 divided by 40 is negative 2. 160 divided by negative 80 is negative 2. Negative 20 divided by 10 is negative 2. And so that gives me a different way to look at this that might be a little easier to manage. Okay, same thing here. Negative 81 divided by negative 27 is positive 3, and so on. So just as we did with the arithmetic sequence, we're going to see if we can figure out what the nth term of a geometric sequence is, and it turns out that we have this formula. Now if you think about it a second, this has some parallels to the arithmetic sequence formula, where we have our first term, a sub 1, and we have our common ratio in this case, where we had the common common difference before in the arithmetic, and then we have our n minus 1. In this case, however, we're multiplying instead of adding here, and we're exponentiating instead of multiplying here. But we've got kind of the same pattern going on. And so this formula here, if we know a sub 1 and we know R, will allow us to plug in a value of n to get the nth term of the sequence. So let's just take a look at a couple of examples. Here I have an example where my first term is 0.5 or 1/2, and then to get from 1/2 to 2, I have to multiply by 4. That gets me to 2. 2 times 4 is 8. Times 4 is 32, times 4 is 128. So we know this is a geometric sequence with a sub 1 equals 1/2 and R equals 4. So there's actually a couple ways I can go about generating this sequence. I can start with my first term and multiply by 4, and then multiply by 4 again, multiply by 4 again, and so on. Or I can use the formula to get whichever term that I want. So in this case, let's get the sixth term. We have 1, 2, 3, 4, 5 terms listed here. Let's see what the next one is. We know it should be 128 times 4, which is 512. Let's use the formula. A sub 1 is 0.5. R is the number that has the exponent. That's 4. And the exponent is going to be n minus 1. We're looking for the sixth term, n equals 6. We plug that in, we get 4 to the 5th power times 0.5. Put that in the calculator, we get 512. Another example over here. We start with negative 1. That's our a sub 1. We multiply repeatedly by the common ratio negative 1/2. So negative 1 times negative 1/2 gives me positive 1/2, negative 1/4, positive 1/8, negative 1/16, and so on. So that generates the sequence 1 by 1. I can skip to the 13th sequence if I wanted to by plugging in numbers into the formula. A sub 1 is negative 1, R is negative 1/2, my exponent is 13 minus 1. Be very careful when you are raising a negative number to a power on your calculator. You need to put it in parentheses because the calculator does order of operations where it's going to do the exponent part first and then put the negative sign on, and that may not give you the correct answer. If you do this correctly, you should get negative 1 over 4096, which is approximately equal to this decimal number right here. Now another thing I want to show you, which is a bit of a preview for stuff coming up in a couple of lessons, is what happens when we have different values for R. And specifically, this sequence here, the numbers continue to get bigger and bigger and bigger. Okay? And the reason for that is because we're multiplying by a number greater than 1. Okay? And even if we had a number smaller or less than negative 1, like negative 2, negative 3, we would have the same situation. So the magnitude of R, the size of R, is what determines that. If we multiply by a number that in magnitude is greater than negative or greater than 1, what happens? We get back a number that's bigger. So every time I multiply by a number bigger than 1, I get back an even bigger number. I'm going to then continue to grow in this sequence and have numbers that are getting bigger and bigger and bigger without bound. That's what we call a diverging sequence. Contrast that with this one. Even though I'm changing sign and alternating through here, you notice what's happening to the numbers. They're getting smaller and smaller. And eventually this sequence is going to converge to 0. Okay, if I pick a big enough number, let's say 13, I get a really small number. And if I keep picking bigger and bigger numbers, I will get closer and closer to 0. So tuck that away for a couple of lessons, but just keep that in mind as we look at these sequences. Some are going to get larger, some are going to get smaller. So let's look at working a couple of examples here. First thing we want to do is to determine whether or not this is a geometric sequence, and if it is, let's find the value of R. So I'm going to just start with any two terms, and these would be the easy ones to do. 6 divided by negative 1. 6 divided by negative 1 is negative 6. So this would be the value of R if this were a geometric sequence. So I have to then go from 6 and multiply by negative 6. I do get negative 36, so that works. Negative 36 times negative 6 gives me positive 216, so that works. And so yes, this is a geometric sequence with a value of R equal to negative 6. Okay, so suppose I wanted to get the first couple of terms of a sequence that was defined with this formula. Well, that's pretty easy. Really all I have to do is substitute my value of n that I'm looking for. So if I'm looking for a sub 1, a sub 2, and a sub 12, let's say, here's how I'm going to do that. This is my n value, so I'm just going to plug that in. 3 to the 1 minus 1 is 3 to the 0 power. Anything to the 0 power is always 1. Now you might notice that this looks like our formula that we just looked at. The problem is I don't have a number out here to match up with a sub 1. But indeed I do, because I can always multiply anything by 1 and not change it. And so a sub 1 equals 1 actually matches this now. A sub 2 comes from just putting 2 into here. So this is going to be 3 to the 2 minus 1, which is 3 to the 1 power, which is just 3. A sub 12, we're going to jump all the way to 12, is going to be 3 to the 12th minus 1 power, which is 3 to the 11th power, which is a pretty big number of 177,147. How about finding the 10th term of this sequence? Well, we got to pick off some things from here. The 10th term tells me that n equals 10. Okay. I know my a sub 1 is the first term in the sequence. That's negative 1. And so a sub 10, the 10th term, should be a sub 1 times r to the 10 minus 1. Well, what is r here? Now, I'm going to assume this is a geometric sequence, so I'm going to go ahead and take 2 divided by negative 1, and that's going to give me negative 2 for r. So a sub 10 should be a sub 1 times negative 2r to the 9th power. Okay, now be sure again that you're using parentheses with your negative numbers raising to a power so that the order of operations makes things work out correctly. And this is a negative 1 here. And when I do all that, I get 512 for my answer.